Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is everything I want to talk about, science and math. And today we are in AP Chemistry doing Unit 8, Acids and Bases for AP, and it's going to be great. All right. So first of all, we have already talked about acids and bases in Unit 4, and in particular 4.8. So when you study for this test, make sure to go back and look at over those at least 4.8, because there could be questions on the test from 4.8. Now, see, a lot of this is going to be review. It's going to be pretty easy. So strong ones disassociate a little bit or completely, acids and bases. Are y'all just not with me today? Y'all are very quiet. You should know this. Strong, you learned this in honors. Strong acids and bases disassociate. Oops, I gotta make it draw. I'll do red again. They disassociate completely. Okay. Remember, and this is something new. For the AP Chemistry test, they expect you to memorize the strong acids and bases. So there is a mnemonic for acids, and it's so I brought no clean clothes. So sulfuric is the so, HI is the I, BR is the brought, HNO3 is the no, hydrochloric is the clean, and perchloric is the close. And that's one that pretty much everybody uses to memorize the acids. Now, there is debate among the bases. So the one that I have seen more than once online for bases is this one. Little Nanny sees and kill rabbits, causing screaming babies. I think it's kind of weird, and it doesn't really help me remember them too much. But lithium hydroxide, sodium hydroxide, cesium hydroxide, potassium hydroxide, rubidium hydroxide, calcium hydroxide, and strontium hydroxide, and barium hydroxide. Now, so one of the things you're going to do after the AP test is I'm going to give you an opportunity to do a project so you can replace your lowest test grade with it. And your project is going to be to make something that's a review, a study thing for next year's class. So they did that last year. They made things for y'all. So when we get to the review point after spring break, our last 2 weeks, we're just going to review. We will get out what they made, and y'all can see if y'all think it's any good or not. But one of the things was one of our students made little laminated things of these to help you remember. And for the strong acids, they did, so I brought no clean clothes. But for the bases, they may have this one. Lily and Nate robbed a bank and kept a crispy spark of cash. Do you like that one better? I forget who robbed the bank. I'm like, who was it who robbed the bank? And I remember Lily, but I forget Nate. But it's Lily and Nate robbed the bank and kept a crispy spark. See, I don't know what a spark is for an amount of cash. So that one's not great either. So y'all can think of a different one, you know? So, because you're gonna need some way to memorize these. You're expected, you don't have to memorize a lot for the AP test, but you are expected to memorize those. So the rest of all the acids and bases are weak and don't disassociate completely. So one of the other things you have to know is about the auto-ionization of water. Auto means self, so the self-ionizing, how water breaks itself into ions. It's a process where water molecules react with each other to form acid and base, hydronium ion and hydroxide ions. And so this is the equation for it. Water plus water makes acid and base, hydronium and hydroxide ions. Now, we can write the equilibrium constant for this, can't we? We leave out the pure water, and so it's just the products, which we go in the numerator, the concentration of hydronium times the high concentration of hydroxide. Now, so that is our equilibrium constant, our equilibrium expression. And it always equals 1 times 10 to the 14th. If you have water breaking apart, that's what its equilibrium constant is. It's so special. You know, we have a bunch of K's now. We have KEQ, we have KC, we got KP, we got Q, which is the same thing. We got KSP, which has to do with dissolving. Well, we got another one. And it's its own K, and it's the K of water. It's called KW, and it equals 1 times 10 to the 14th. What about that number seems familiar? Maybe the 14? Where do we see 14 in here already? That has to do with acids and bases. It's the pH, right? The pH scale goes from 0 to 14. Guess where they got it from? They didn't pick that number out of a hat. They got it from there. So that's why we're going to learn more about that, but that's what now. This is the KW only at 25 degrees Celsius, room temperature, and it's, because you remember Ks are always determined by temperature. It always gives us a temperature and we ignore it because it's not any of our math that we're doing for these. Okay, so here's an example problem. At 25 degrees Celsius, we don't care. The hydroxide ion concentration is 5.3 times 10 to the negative 8. What is the concentration of the hydronium ion? So if you have a problem like this, notice they do not give you the KW. You are also supposed to memorize that. So they'll give you a question like this. You would just fill it in and solve for your unknown. And I got 1.9 times 10 to the negative 7. Okay, that's not hard, is it? Only hard thing is a bit of memorization. You got to memorize the acids, the bases. You probably need to memorize that equation. You probably need to memorize that number. All right, pH. Now this is straight out of my honors notes. I just copied them because you should have already learned this in honors. pH tells how acidic or basic something is. What pH is it's the negative log of the hydrogen ion concentration. There's also pOH, which is the negative log of the hydroxide ion concentration. And if you add pH and pOH, you get 14. They're not that number. So I want you right now to try on your calculator these problems. We have a hydrogen ion concentration. I want you to put in your calculator. I want you to take its negative log that number, and tell me what this pH is. We're going to do these together just to practice them real quick. So what'd y'all get? Do negative log 0.0235, enter. Did you get 1.62? If you didn't, mess around with it, figure it out. That's what the other class got. I didn't actually do these. The other class did it and I wrote them down. We're assuming they're right. Okay. What did you get? You got something different. Well, let me do it myself. Let's not trust those first period AP chemistry students. Let me get my calculator and take its negative log. Negative log 0.0235. That should be it. I got 1.62. If you're getting the wrong answer, check your calculator under mode. See that button there? Make sure that you're in degrees, not radians. If you're doing your calculator right and getting the wrong answer, that is often what's wrong. Okay, for the next one, I got 219. So I want y'all to do these and check your answers. Y'all check that one, and then we'll talk about the next one. I started to rush ahead. I don't want to. Okay, did y'all get that one? I see some yeses, some nods. Okay, so how about this one? This one we don't have to do in our calculator. This one we can do in our head. Does anybody know what the negative log of 10 to the negative third is? What?
10 to the negative 11.
What?
10 to the negative 11.
3.
No.
3.
It's 3. Because if you know what, remember that logging is the opposite of exponenting to the 10th. Just like adding is the opposite of subtracting. So the negative log of that number is just going to be 3, no exponent. So if it's 1 times 10 to a number or just 10 to a number, you can just look at it and get the pH and don't have to put it in your calculator. but only then. Otherwise, you got to put in your calculator. Okay, so just like how you can have pH, you can have POH. So somebody take the negative log of 0.0035. You should, what the other class got was 2.46 and 4.35 and 5.7. So check those on your calculator and see if you got them. Your book is over there. You're welcome. Did they do them right? Are we getting the same answers they got? I see some nods. Okay. So the other thing you have to know is that pH plus POH equals 14. So if you know one, you can solve for the other one. So on the AP test, you probably can just about bet that you will have a pH problem because they can ask you so many things. They can get you to solve for the hydrogen ion concentration, and then you can take its pH, and then you could get the POH, and then you could get the concentration of the OH. So how you do these, you just subtract from 14. So if pH is 3, what's POH? What's 14 minus 3? Somebody said it, 11. So 14 minus 10 is 4. 14 minus 8 is 6. Now, if you know the pH, you can get the concentration. It goes back and forth because the opposite of log is antilog. And what an antilog is doing 10 to the negative x. So here's an example. If our pH was 1, then we could do 10 to the negative 1, and our concentration, our calculator will give us is 0.1. Don't you feel smart taking antilogs? Oh, what were you doing in math today? Oh, just some antilogs. You know most people don't have no idea what you're talking about. All you're doing is taking 10 to the negative of that number. But it sounds much fancier to say it's antilogs. So y'all try the next one. Take the antilog of the pH, which is 9.58, and see if you can get the concentration of hydrogen from it. I got 2.63 times 10 to the negative 10th. Did y'all get that on your calculator? Yay! This is a great skill to have. Okay, so pH scale, acids are 0 to 6.9. Actually, acids can be less than that. You can get a negative number. So if you do a problem and you get a negative number for a pH, don't freak out. It's possible. If it's really, really strong, it can actually be less than 0. Water is 7, and bases are 7.1 to 14. Y'all learned that in honors. So next we have a little graphic of the pH of some common substances. And you had that in honors too. We've got bleach at 12. We got eggs at 8. We got water at 7. We've got coffee at 5. Tomato juice at 4. Lemons at 2. Like that. Now, if you raise the temperature from 25 degrees Celsius, the kW goes up. And if you lower it, it goes down. So, but changing the temperature does not change the acidity or basicity, just the scale. So that makes sense. If you heat up lemon juice, it doesn't suddenly change its pH. It's still going to be acidic, right? If you chill it and make some lemon ice cream, it's still going to be very lemon sorbet, something like that. It's still going to be very acidic, right? But it does change the scale. Okay, 8.2. Look, we're just rocketing along. 8.2. pH and POH are strong acids and bases. Okay. If you are given the concentration of a strong acid or base, you're going to use that as your ion concentration. The concentration, okay, let me explain what I'm saying. Say that instead of telling you the hydrogen ion concentration is 42. They say instead the concentration of hydrochloric acid is 42. You just use 42. The concentration of the acid is the concentration, or the base is the concentration of the ion, unless It's multiprotic. Let me explain what I mean. So this is called diprotic. Di means two, pro means proton. This is sulfuric acid, and notice how it's got two H's. You see that? If it's something that's got two on it, like it could be two hydroxides, magnesium hydroxide or something like that, you first, before you use that concentration they give you, you multiply by the subscript of how many acids or bases you have. What makes it acids are those H's coming off. It's got two of them, so you multiply that concentration by 2 first. If you have a very dilute acid, something like 1 times 10 to the negative, for a concentration of like 1 times 10 to the negative 14, and you take its negative log, it can give you a number that says it's a base. Does that make sense? Could an acid have a pH of a base? No, it does not. And the answer, and it is wrong. I know this is very disturbing. You have gone your whole life trusting math, as math should be trusted. But math can mess up on this because it is a logarithmic scale, and sometimes that causes problems. So if you do your math and you get the pH of an acid as a base, it's wrong, and instead you just say the pH is 7, which is neutral, and really it should be slightly less, but that's what you do. That's just the answer. I'm just telling you the answer. That's the answer. If you get a negative pH, if you get a base pH for an acid, just say it equals 7. It's just how it's done. Okay, sometimes you have to add 2 acids and get the pH. So here's the example problem. You have 0.1 liters of a 5.5 molar hydrochloric acid, and you add it to another acid, 0.2 liters of a 3 molar nitric acid. What's the pH? So multiplying the volumes to the concentration will give you moles, and then you add them together to get the concentration, and you can take its negative log. So here you do 0.5 times 0.1 is 0.05, and 0.2 times 0.3 is 0.06. You add them together and it's 0.11. So then you're going to take the negative log of this number of moles, 0.11, divided by your total amount of volume, which is 0.1 plus 0.2 is 0.3, and take its negative log. So really, if you just think about it and go, hey, I need a concentration, how am I going to get it? I'm going to need the concentration of the whole thing with the whole volume. You can almost just figure that out in your head. But the answer is 0.44. Another thing about this is you don't have to solve this before you put it in. You can put in your calculator negative log, beginning parentheses, 0.11 divided by 0.3 in parentheses, and it should give you the answer. Y'all can try it, but I think it will. I don't think you have to do the math and then put it in. Not that it's hard, especially if you use that answer button on your calculator. Okay, we're rocketing along to 8.3. So weak acids and bases, most acids are weak, all except the ones you're memorizing, so I brought no clean clothes. So an example of a weak acid is acetic acid. Vinegar is made from it, and water. So here's a reaction between acetic acid and water. This is its conjugate base. The conjugate base is always the acid minus the H. See how that's the acid? Now this is an organic acid, it says Cu. Organic acids are going to have that Cu in it. They're not just cool, they're Cu. That's how you remember it. They say Cu. All right, so there's our Cu. It lost its H, there's its conjugate base. So that means this was the acid. That means water was acting as a base, and its conjugate acid is always whatever the base is plus the H. That one is going to lose the H, that one's going to get the H. So you need to be able to understand equations like that and label them. And then we were given the Ka, our K for A, and it's a number. This K, okay, so we've learned KEQ, KC, KP, KSP, Q, KW, and now we're adding another one. And remember, they're all the same thing. Products over reactants raised to the power of their coefficient. This one is Ka. It's telling us how much an acid dissociates. Okay? And that's why it's just another K. They're all the same thing. Okay? Now, just like other Ks, The larger the Ka value is, the stronger the acid is. The more it is disassociating, the more this reaction is going toward completion. All this is making sense, isn't it? Nothing's hard. We're taking old ideas and just putting them together for this unit. We have one new little formula, but other than that, we are just mostly thinking about old things in new ways. So just like all the other K's, we can write the expression, products over reactants raised to the power of the coefficient, but of course remember, leave out that pure water, it's not in the denominator. So we have a question here for our acetic acid. We were given the equation, we were able to write the Ka, we were given the value of Ka, and they ask us what is the concentration of a 0.75 molar solution of acetic acid. What's the acid concentration? So we're going to use an ICE table. Yay! You loved them last unit. You were sad to see them go. Don't be sad. They're in this unit too. And we're going to do them the exact same way. So we write down our starting amount, 0.75, and starting, these are zeros, right? What is our change going to be? What do we write on the next line? What letter do we write on the next line? X, and this one's going down, so is it positive X or negative X? Negative X, I'm getting hand signal answers. So these are going to be what kind of X? Positive X. Yeah, see, you do know how to do this. Now what do we do next? I got a line to tell you to do it. We're going to add them. I like to put my little plus over here. So 0.75 minus X, X, X. Now we've got our expression here. We fill in our answers. Now notice that our K is 10 to the negative fifth. So we get to mark out that X, just like we did last time. That's always fun. It makes the math easier. And then all of this is equal to our given Ka. Those times 10 to the negative fifth, and that's why we could ignore it. And now we are going to solve for X. And to do that, this is X squared, so we can just take divided by, we're going to take our 0.75 and we're going to multiply it. That's X squared. We take the square root of both sides and we get the answer. Are y'all following my math here? And it is 0.0367. Then, after we got that concentration, they can ask us, well, what's the pH? Do you see how this lends itself to free response questions? They can ask us 10 questions about the same thing. Write the expression, write the net ionic equation, figure out the concentration, figure out the pH. So now we take the negative log of this, and our pH is 2.43. Another thing they can ask us to do is to calculate the percent dissociation. So, and that means the percent that is going down. So we take our concentration and divide it by how much we started with, or concentration of X, and times 100. And so here our the answer is 0.49%. So see, isn't that a beautiful free response? That's just ready to go. Okay, keep it going. Here's another example problem. Hydrofluoric acid is a weak acid that partially disassociates from water according to the following equilibrium expression. Okay. They told us the acid dissociation constant. They want us to write the expression, products over reactants, leave out the water. What is the concentration at equilibrium and pH at percent dissociation if you have a 0.6 molar solution? So we start with writing 0.6 molar, because that's what we start with, 0, 0. We leave out the water. It's not important. Sorry, I scrolled too much here. Okay. It goes on to the next, then we do the change. So just like before, our change is minus X plus X plus X. And then we write down the difference, 0.6 minus X, X, X. We fill it into our equation. There's a denominator line there. Okay, but this time, our Ka was too big, wasn't it? Yes. Do you see that -4? You see that? So we cannot mark out the x. We're going to use our calculator to solve for x, just like how we did last time. We're going to do it on our graphing calculator with 0 in this equation. We'd do minus 6.8 times 10 to the -4th on one, y equals 0 on the other one. Graph it, go to second trace, intersect, enter, take the positive answer, not 0 or not negative. Okay? So if you didn't learn how to do that on your calculator last time, guess what? You can do it this time. So with our calculator, we got that answer, 0.02. Then they asked for the pH, so we did the negative log of 0.02, and I got 1.69 as the pH. And then we can also do the percent dissociation again, which is going to be 0.202 divided by 0.6 times 100, and that's 3.4%. Okay? Sometimes you're asked if you've got a diprotic, see those two H's right there? Sometimes they'll ask you to write the two net ionic equations for it. So first you make one H come off, and then you take that and stick it over here and do it again to make the other H come off. Now they won't make you do the ice table again, because if you did and you added those H concentrations together, looking at sig figures, the number doesn't change. The second one does not contribute much at all. So you won't have to do that. But if they ask you why don't you have to do it, it's because the second H coming off does not change it. It won't change it with sig figs. Okay, you do it the same way, but they won't have you do the icebox twice. The amount that disassociates the second time is too small to matter. Your number will not change. It'll be the same number. You just write it down twice. Okay, what about weak bases? Sometimes instead of weak acids, you're given weak bases, but that's a little bit rare on the AP test. Usually it is weak acids that they do stuff with, but be ready, it's the same thing. So weak bases, most weak bases have NH in them, and it's the unshared pair on the N that's ready to accept a proton. Bronsted-Lowry, that was our warm-up. So here's an example problem. Consider a 0.4 molar solution of ammonia. The base dissociation, so now we got a new one. You knew it was coming. If there's a Ka, there's got to be a Kb, right? The base dissociation constant is this number. Write the Kb expression for the base dissociation equation, solve for the concentration, calculate POH and pH. We can do both. So same thing, you write your formula, your net ionic equation, you fill in what you're starting with, 0400. Let me get to this. So we're going to do minus x plus x plus x. We add them up. 0.4 minus x, x, x. Okay? And now look at our Kb. Are we going to get to ignore that? Ooh. 10 to the -5th. I see some ignoring in my future. Okay? We write our equation, and we already did that, and we fill it in, and we can mark out the x, because it was 10 to the -5th, yay! So now we just multiply by 0.04, and multiply these together, square root both sides, and x equals 2.68 times 10 to the -3. That is the concentration of hydroxide. We take its negative log and we get the POH as 2.57. We subtract it from 14 and we get the pH is 11.43. That's a very basic pH. We can get the percent dissociation by how much we started with. That's our X. How much we finished with, how much our change was, divided by how much we started with times 100, and I got 0.67%. Okay, so here is another little factoid to know, that if you multiply a Ka and Kb, you get Kw. And I think that is another equation that is on your AP reference sheet. And you also need to memorize that at 25 degrees Celsius, Kw is 1 times 10 to the negative 14. So sometimes they'll give you a problem where they'll give you 1K and you solve for the other because you memorized 1 times 10 to the negative 14. Now, you need to know what these K's mean, that if it's a small Kb, it's a weak base. And it will have a conjugate strong acid. When one is weak, the other is strong. If you have a large Kb, it's a strong base. And it will have a conjugate weak acid. When one is weak, the other is strong. It sounds like a moral, talk where they're encouraging you to encourage other people. When one is weak, the other is strong. Doesn't it? Be strong for your friends. We can make a little speech out of this. When your friend is weak, you be strong. Be like an acid and a base. Be like a conjugate. There you go. Acid-base reactions and buffers. If you mix a strong acid and a strong base, the net ionic equation is always the same. Acid plus base makes water. And notice the arrow is only going in one way. It goes to completion. If there's anything else in this equation, it's the spectator ion. So like if you added hydrochloric acid and sodium hydroxide, this is the net ionic equation, and the chlorine would be spectator and the sodium would be spectator. Do you see that? So that means, remember, that's just floating around in the beaker, swimming around, having a good time doing nothing. Okay, here's an example problem. A student adds 150 milliliters of nitric acid to half a liter, to the strength, 150 milliliters, 0.5 molar nitric to 300 milliliters of 0.3 molar sodium hydroxide. Write the net ionic equation. Well, these are both strong, so we know the net ionic equation is that, okay? And then it says, list the spectator ions. Well, it's the stuff that's not H or OH. So on this one, the NO3, and on that one, the Na. So spectator, NO3, and Na. Next, we wanted the moles. We gotta get the moles so that we can get the concentration, so we can get pH. Okay, so for our hydrogen, we take our number of liters. We had to change milliliters to liters. Multiplied times mole per liter, and then the liters cancel out, and you're left with moles, 0.75 moles. Then you do the same thing with hydroxide. Multiply the liters times the molarity, which is moles per liter. Liters cancel out, and you're given the number of moles. Notice, this is less and this is more. That means the less limits. Remember when we did stoichiometry and talked about the limiting and excess reactant? That is actually important again here. So this is what's limiting it, the one that's less. So next, we write down our ionic equation. We write what we start with, 0.750, 0.009. Our water doesn't matter. Remember, it's a pure liquid. So we don't deal with those. So now we tell the change. Because whichever one is less, that is your change. Because your other one's going to be in excess, it's not part of the reaction. So for this one, we're not going to put X, we put how much we know that our moles are being used up. So it's minus, for both of them, 0.0750. And then we add these up. That is 0. This is 0.0150. Now, why are we doing this? You're thinking, I have no idea. The reason why we're doing this is they asked for pH. If both of these were used up completely, we know the pH is 7. But they ask us for the pH on the AP test, So probably something more is up than writing down 7. So what you're really trying to find out is what got left over and what is its pH. That's going to tell us what's its concentration, and from its concentration we can get the pH. Now do you see the big picture of this problem? Yes or no? Do I need to say it again? Anybody want me to explain why we're doing this problem one more time? Okay, y'all seem to understand. Okay, so now we've got these, and we need to find our total volume. So it's 0.5, our total for where we started with, because to get our concentration, you have to have volume. So we add up our two volumes, and it's 0.450. Then we can get our concentration of hydroxide. So it's this much hydroxide that got left over that's floating in our beaker, divided by the total volume, and it's 0.0333. Now we've got the concentration of hydroxide, we can get the pOH by taking the negative log, and it's 1.48. Now we're finally getting somewhere. We've got the pOH, we can get the pH, because 14 minus the pOH is equal to pH, and done, we got the answer to this big fat problem. It's 12.52. Put a box around it, because we are done. But you can see how that can be a free response question, don't you? Because it's got lots of parts that they can count each part. Okay, now what happens if you mix a weak acid and a strong base? What do you think you're going to be left with? It's going to be more base, isn't it? You mix a weak acid and a strong base, you're going to have leftover base. Let's get to it. So this is the equation. This is the weak acid, there's its H on it. That's the strong base, hydroxide. It makes water and the conjugate base of the weak acid. Remember I just told you it would have base in it? There's the base right there. That's a conjugate base. Remember the conjugate base of an acid is you just take the H off and put a charge on it. If there's not enough OH to use up all the weak acid, you'll have a mixture of the weak acid and its conjugate base. So if you didn't have enough of this, some of that's left over, and you end up in your beaker the weak acid and its conjugate base. Okay, so that leads us to our next topic, buffers. Does anybody know what a buffer is in chemistry already? Sounds like you're working out. You're buffer. I'm buffer than someone who doesn't work out. That has nothing to do with it. But buffers, they are a mixture of a weak acid and its conjugate base. It's exactly like that. Okay, let me find my little buffers thing. Oops, streaks of acid. Here we are, we're right here. Okay, so what do buffers do? It resists changes in pH. They are very important, especially in your body, especially in your blood. You could not have your blood changing pH and still be alive. So there are buffers in you right now working. You drink a lemonade, you're not going to throw your blood into acid state, okay? So you eat a little soap on accident, you're not going to suddenly have base blood. The buffers in your blood are going to take care of it. So if you have a strong acid reacting with a weak base, you can have it. It's rare in AP chemistry. They don't usually do it. They usually like the weak acids and the strong bases, but there is an equation for it. Here's the acid, there's the base, there's the water, and there is the conjugate acid of the base. This will also make a buffer if it's not all used up and you have a mixture of weak base and its conjugate acid, but this is rare in AP Chem. So just to know it exists. Now, what about the strengths of acids and bases? And this goes back to our learning target, that we are going to be able to recognize acids and bases, and in particular, how strong they are. So on the AP test, they can ask you, which of these is stronger, hydrochloric or hydrofluoric? And you're thinking, I don't know. Well, I'm going to teach you how to know. In the following reaction, which base is stronger, CNO or H2O? So here is a reaction. We got water. We've got this HCNO. We've got acid, H3O, and CNO ion. And we have an acid dissociation K there. So, and this is a number. It's small, so this is how you know. How you know what's going on here. You look at this and you go, this is small. My reactants are going to be favored. Even though this is a equilibrium, mostly this is what is being pulled to. So this CNO is accepting hydrogens. So it's getting hydrogens and it's keeping them and zooming over here. That is what's happening. It's going that way. Can you see that? This is getting an H. Shoom, it goes over here and becomes that. Okay? Water is not doing as good of a job where it would be getting an H and coming over here and being that. Do you see that there? It's not doing it. This side is favored. And so therefore, let me get this right, our CNO is stronger because it is grabbing H's and that one's not. So CNO is a stronger base. It's doing a better job accepting protons than water is. So sometimes instead of telling you the Ka on these problems, they'll just draw an arrow in one direction instead of the equilibrium arrow to show you for you to be able to answer that question. Okay, can you understand it? You just think of who's better at taking that proton. Okay, next, acid-base titrations. We did one back in Unit 4, but we're going to learn a little bit more about them. But it's not hard. You're going to do fine. We're doing great. Okay, Unit 8.5, acid-base titrations. Okay. An acid-base titration is a way of finding the concentration of a solution, acid or base. And if you remember, that's what the setup was. We had acid in the bottom, base in the burette. You let it through, turn pink. If it's that pink, you overshot the equivalence point. And that's what y'all did, right? When the reaction is complete, there's a color change, and you have reached the end point. When the moles of acid equal the moles of base, it is also called the equivalence point. Now, it's a little bit different, but people tend to interchange those terms. Okay, so this is our new thing. All of that was kind of old. So this is our brand new thing. Yay! And it is the titration equation, and it is great because when you go to college and do titrations, it can make your life so much better. Okay, now why? So this is the titration equation. Molarity times volume of your acid equals molarity times volume of base at your equivalence point. Now, if it is diprotic, before you do this equation, you have to multiply it by 2. Same if it's like OH, you might have to multiply by 2. So sometimes this equation has a 2 in it. I think this equation is on your AP reference sheet. Example, a student performs a titration to determine the concentration of hydrochloric acid solution using sodium hydroxide of a known concentration. So your unknown's in your Erlenmeyer flask, your known is in your burette. A 25 milliliter sample of the hydrochloric acid is, so you know your volume of your acid is titrated with a known molarity of sodium hydroxide, 1.50. The endpoint of the titration is reached when 35 milliliters of sodium hydroxide is required to neutralize the answer, and the acid. What is the molarity of the hydrochloric acid? How many moles of sodium hydroxide were used in the titration? So that's our questions, and this is how we're going to answer it. First, you label your knowns and unknowns. We've done this in every problem going back to honors, haven't we? So the molarity of HCl, we all know. That's our X. All right, we have our volume of acid, our volume of base, and our molarity of base. Notice you can leave these as milliliters. You don't have to change them to liters because it's a ratio, and with ratios, you don't have to bother with that. You probably remember that from when we did the gas laws in honors. Y'all remember that from gas laws and honors? Okay, so there's our equation. You put in an X, you put in all your knowns and unknowns, and you solve for X, and it's 0.210. Okay, So now we know the molarity of our unknown. Step 2, they want to know the moles of NOH used. So we've got the number of moles of our NOH, and that was big M, so that's moles per liter. We can multiply it times the liters cancel out. This is just like that other problem we did. And we can get our number of moles is 0.00525. This is useful to calculate. So this is really useful. And this is why you're going to love this equation. When you go to college and you are going to do a titration, instead of sitting there for your whole big burette going drop, drop, shake, drop, shake, drop, shake, you can often use this equation, find out what your volume's gonna be before you do it, zip down to right before it. Don't go all the way, that's living on the edge. Go right before it and then start your drips. Drip, shake, drip, shake, drip, shake. And then you get down all your data, write down how much went down, and you're out of there while everybody else is going drip, drip, drip for hours. So my kids are like in college right now, and that's one of their favorite things is to understand the stoichiometry of titrations before you go in, mathematically get the answer before you do the lab. It's a 10-minute lab, while everybody else is going to be cussing and fussing because they overshot the equivalence point and they're having to start over for the 3rd time because the phenolphthalein went pink again, right? Some of y'all had that frustration last time. I heard a little bit of cussing and ignored it because titrations might bring it out in you. Okay, so next, strong acid plus strong base. Okay, so you need to know if you have a strong acid and a strong base, you get water, and what's the pH? We learned this in honors. What's the pH of water? 7. Okay. Now, we graph these. This is the new thing, is we graph, these are called titration curves. See how they're all curvy? If you have a strong acid and a strong base, this is the graph. You need to know that. You start off with a very low pH with your acid, then you get, it shoots up, and then you get to a very high pH of your base. If you look halfway on the vertical stick and go over, it tells you the pH. Oh, it's not wanting to do. It'll tell you the pH, and you can see it's a little hard to read, but it's 7. Do you see that? So you can, so that is, this middle part right here is the vertical line, is called the inflection point, and it's the pH at the equivalence point. So so we know strong acid, strong base makes water, pH is 7. Halfway through the vertical stick, you can go over and see what the pH is. Now, but what if it's a strong base and a weak acid? Strong base, weak acid. Okay, it's this one. Do you see that one? Notice it's higher up. Notice our pH is over 7. Do you see that? Everybody see that? So if we were given this graph and not told, we could look at it and go, oh, this is a strong base and a strong acid because my equivalence point is a base. We could label that diagram, couldn't we? Okay, and that's how they all work. Okay, so here's a strong base and a weak acid. Here's our acid. There's our strong base, sodium hydroxide. This is the conjugate base and water. So here's the example problem that we can also do using our titration equation. If 1 mole of 0.1 mole of molar sodium hydroxide is titrated into 30 milliliters of 0.2 molar weak acid here, determine the volume of sodium hydroxide needed to reach the equivalent point. Determine the pH when 30 milliliters of base have been added. And this is your Ka. All right, so we have our equation, our titration equation. We fill in our knowns and unknowns, 0.2, 30, 0.1, and X. And we get the X is 60 milliliters. Okay, so if we do this titration, the amount of a base that we let go out of our burette was 60 milliliters. But then they didn't ask us what was the pH at 60. They asked us, well, what's the pH at 30? Now, 30 is half of 60. So this is a special point. It gives us special information. It's the halfway point. It is so special. At this point, pH equals pKa. Now, what does that mean? Okay, what it means is, if you have pH, you take the negative log of H, right? So pH means you take the negative log of H to get that answer. pKa means if you take the negative log of Ka, you can get pH. In math, P means, and I have no idea why, take the negative log. Who came up with that? P means take a negative log. Okay, but that's what it does. So pKa is the negative log of the pKa. So what this means is that if you have the graph and you go halfway on that bottom part before it becomes a vertical line, you can go over and see what that pH is. Then you can mathematically from there get the Ka. You can solve for Ka using this information. So sometimes you have to do that. Sometimes you gotta solve for the Ka. So here we take our negative log of 1.8 times 10 to the negative fifth, and we can go, it goes both ways because they're both equal to each other. Then you can get the pH at the halfway point, and this is 4.74. So sometimes you can get the Ka from pH, and sometimes you can get pH from Ka. And I'm pretty sure that equivalence is on your reference sheet. But if not, you just got to memorize it. That halfway little point is special. Now, let's talk about what if it's got more than one H that comes off. It gives us a fancy graph like this. Look at this. It gives more than one curve. So this will be something that is triprotic, because it had 3 H's that came off, because it's got 3 straight parts. Do you see that? So this would be like H3SO4. So first it starts off all your H3SO4. Then one H comes off and it's H2SO4. Then another one comes off and it's HSO4. And then it's all used up and you have overshot it and you've only got OH and it's all pink and you went too far on your titration. Okay, so this is what this means. You can have more than one curve and it just means there's more H's on that chemical. So you can estimate the first pKa by the first equivalent point. So like if you want the pKa of this part of it, you look halfway and then you can figure out what the pH is and then do the negative log and you can get the pKa. For your next one, you take this one and you take this equivalence point and that one and you divide them in half and you can get this midpoint. If you have this one and this one, you divide it in half and you can get that midpoint. So the next will be halfway between the equivalence points. So sometimes you have to look those up. We'll get to do some problems. I'm sure we're going to have some on our I do, we do's. Sometimes they ask you which ion is most prevalent at a certain point. You just take off one H per section. The top part is all base. It's all OH. So let me say that again. So you would start down here, and what would be most prevalent would be H3SO4. Here, H2SO4. Here, HSO4. Here, OH. You went too far. Okay, you might have to label that. All right, 8.6. Molecular structure of acids and bases. Right here. Okay, so what makes an acid or a base strong or weak is its structure. And we're going to learn some rules. They're going to give us 2 acids or 2 bases, and they're going to say which is stronger, and this is the answer. This is where you're going to get it from. So the structure determines the strengths of acids and bases, and it's based on Coulomb's law. Does anybody remember what Coulomb's law has to do with? We learned this when we very first started AP Chemistry. Anybody remember it? Coulomb's law. I think Coulomb is fun to say. In physics, Coulomb is a unit. In electricity. All right, so what it has to do with, I'll just remind you, that it's how the force between particles has to do with the particle size and the distance between them. Remember that? The bigger particles can't get so close, but little particles that are close are stuck really hard. Particles further apart, stuck not so hard. Big particles can't get as close, stuck not so hard. That's Coulomb's law. Little particles close together, they're going to be stuck really hard together. They're going to have a high force of attraction, and they're going to be harder to separate. That's what we learned before. So that is what has to do with this. Because remember, the strength of an acid is how much it disassociates, how easily it gets pulled apart. So small distances between atoms means high attraction. It doesn't disassociate much, so it's a weak acid. Strong acids disassociate completely. It has a high force, weak acid. Large distances between atoms is low attraction. It disassociates completely. It would be a strong acid. The stronger the acid, the weaker the conjugate base. Remember, I told you that was our motivational talk. Be strong when your conjugate friend is weak. Okay, why? Think of it as competition for H. It's sort of Le Chatelier. If you have an acid with one H and O and another atom we're going to call X, the acid that has the more electronegative X is the stronger one. So there is a connection between electronegativity and strength. Also, if you have a chemical that has more O's in it, more oxygens, it is going to be the stronger one. For organic acids, remember they say Cu, they are attached to the rest of the molecule that is designated the letter R. The more electronegative R is, the stronger the acid is. I want to draw this and make sure y'all understand it. Okay, so an organic compound has got a carbon, organic acid, carbon, double bonded to oxygen, single bonded to a OH. Do you see how that's Cu? That's what Cu looks like. If you see that on something, it's an acid. Okay, this will be joined to something else. It could be joined to another carbon with some hydrogens on it. This is ethanol. This is the alcohol people drink. I don't. I got too much alcoholism in my family. In my family, you're either an alcoholic or you don't drink. So I decided to not drink. When I was 14, looked around the family reunion and thought, nope, not gonna do it. So if y'all ever done that, looked around the family reunion and made a big life choice, I did it at 14. It was at my grandma's house. Okay, anyway, back on target. This is called R. It's just designated R. Whatever the Q is attached to is called R. Just like, in math, X is what you don't know. In organic chemistry, the rest of the molecule is called R, and whichever R is more electronegative, that is going to be the stronger organic acid. Okay, so let's see if we can do it. Okay, so which of these two is going to be a stronger acid? Which R is stronger? Which one is more electronegative? Which is more electronegative, an F or an H? An F. Y'all are being so shy. You're whispering your answers. Be confident. Confidently say the wrong answer out loud. It's okay. We won't judge you. Okay? So how about this one? Which is going to be stronger? Here we got H, O, and another thing, Br or Cl. Which one is more electronegative, Br or Cl? So I saw that whisper, Cl. Y'all are so shy. Okay, how about this one? Which one is going to be stronger, H2SO3 or H2SO4? The one with more oxygens, right? It's got more oxygens. Okay, let's try our last one. Next page. Which one is going to be stronger? HI or HCl? Yes, because more electronegative, right? Okay, so you can have questions like that on the AP test. Okay, here's another one. You can have a strong base with a weak acid. I actually showed you this one. Notice the equivalence point is greater than 7. So that way we know, we can look at that curve and know that that is a strong base with a weak acid. We know that it's not a strong acid and a strong base because the curve is softer looking. It's sharper when it's a strong acid and a strong base. Yes, sir?
I just want to reconfirm. So like for electronegativity, the closer it is to fluorine, the more
Yep.
electronegative.
Fluorine is the most electronegative, and the closer it is, the higher it's going to be.
Just wanted to make sure.
Yep. Okay. So now notice our halfway point. There's our halfway point. We could go over, and from that we could find the pH of the halfway point, and we could get the Ka of the halfway point. Okay. And at the halfway point, you have weak acid and its conjugate base. So it hasn't been neutralized yet. What's floating in our beaker right here is acid and base. Does that make sense to you? So we've got acid and base here. It hadn't happened yet. So for these little, and also pH equals pKa there, so we can do that math. Okay, so sometimes you are told to select the correct indicator. You want one that's going to turn colors at the right point. So like we wouldn't want phenolphthalein for this because it's not turning at 7. Phenolphthalein turns at 7. But so we got to find another one. You will be given bases, you will be given indicators, and you have to pick the one that changes at the right point. Sometimes you have to go, well, if I have a strong acid and a weak base, if a strong acid and a weak base, then I need to pick something that is going to change at a point that's less than 7. Or if I have a strong base and a weak acid, I need something that's going to change at a point greater than 7 so I can get it. So here we have a list of all these different indicators, and if we were going to pick the right one here, we would need one that's like about 8. We come down here and it looks like it's thymol blue is what we should choose. That is an easy question, isn't it? What's the right indicator? Okay. So next, buffers. We've talked a little bit about buffers before because I'm buff. Okay, so a buffer is a weak acid with its conjugate base. It can be vice versa, but it's usually that. So we want to know, is this a buffer? A weak acid conjugate base. Is this a buffer pair? You think yes or no? All for yes? All for no? You are correct. It is no. Why? H2SO4, is that strong or weak? It is strong. So this is a strong acid. It's got to be a weak acid. So that's not it. OH, is that strong or weak? NaOH, strong or weak? Strong, right? So this is no. This is a strong base. It's got to be a weak with its conjugate. Weak and a conjugate. So here, that's weak. That's its conjugate. Yes. That's what you're looking for. Now, how does it work? How do buffers make it where it resists changes in pH? If you add an acid, it'll react with the base. And if you add a base, it's going to react with the acid. So whatever you add can get neutralized to a point. Eventually, it can't handle anymore, and you'll blow it out. You'll blow out your buffer, but it works for a while. Okay, how do you calculate the pH of a buffer? Well, we have a special equation called the Henderson-Hasselbalch. Okay, so here is an example. A student obtains a buffer containing 0.6 molar HF, remember that's weak, and 0.2 molar NaF. This is our Ka, and we want to calculate the pH. This is our equation, and this is on your AP reference sheet. pKa plus log of the concentration of the conjugate over the acid, okay? So we could fill this in. We were given our pKa. We put in our NaF in the numerator, our HF, our acid in the base, and we get, where did I get it? pH and solubility, buffer capacity. Oh, it's right. I'm like, I lost my paper. Okay, it equals 2.66. Next, buffer capacity. This is what I already said. If the buffers are dilute, they can't do their job as well. If they're too dilute, they will exceed their capacity to neutralize. If a buffer has more conjugate acid than base, it can absorb more base without the pH changing significantly and vice versa. So, whichever half of it's strong can go a little bit longer before it gets overwhelmed. Okay, last section, pH and solubility. pH and solubility are related to each other. That makes sense because it's dissociation. So here I have magnesium hydroxide. It's dissociating into magnesium and hydroxide, and it has a KSP that is very small. So that means it's not going very much to products at all. You can decrease the solubility by raising the pH, adding a base with OH. The reaction will shift left. Okay, so if I decrease the solubility by adding a base, which makes sense, the base is trying to come off, but I'm adding more, I'll make it go that way, it goes less. But if you add acid to this one, it will react with that should be a superscript, the 2F, which will make it come out of the solution, and then that makes a void, and the solution will shift right, and more will dissolve. So that's really just an application of Le Chatelier with acids and bases. Science is great.